Hey everybody, in this video we're going to be using Euler's method, sometimes called Euler's method. Euler's method, it's a numerical approach to approximating a particular solution of a differential equation. Up until this point we've been given a derivative and we could separate the variables, and given an initial condition we could actually solve the differential equation, meaning we could find the antiderivative, we could find the solution, the original graph if you will. But what happens when you can't separate the variables? Okay, we have to have a different method for approximating the solution. Euler's method is usually used for those such cases where we can't separate the variables and find a solution curve. Euler's method, what it does is it allows us to generate some ordered pairs that might not be on the actual solution curve, the antiderivative, but they're close enough to where when we sketch these and connect these points that we're actually modeling the solution. So you could use Euler's method with a separable differential equation, meaning one that you could separate. You could use it with them, but certainly without them too. So it is valuable because you can use this for all differential equations. Now, in order to use this Euler's method, you're going to have to be given some certain things. You're going to have to be given a derivative. You're going to have to be given an initial condition, a point on the regular graph, and you're going to have to be given an increment, a delta x, a dx, if you will. All right, to understand what we're doing, I'm going to draw a little graph and kind of get our minds around why we're going to generate these points and what it does for us. In order to understand Euler's method, let's get a graphical representation of what we're finding. Let's say that we had some slope field, and the slope field suggested that our solution curve looks something like this, according to the short slope segments. Okay, I'm going to pick on the point 1, 3. We're just going to imagine that this is the ordered pair 1, 3 for right now. Okay, remember you're going to be given an initial condition, so given an initial condition, a point on the graph will at least start with an ordered pair. All right, so remember with Euler's method, what we're going to do is we're going to generate some points. We're going to plot these points, and when we connect them, we're going to say, you know what, the connection of those points resemble the solution curve. So our problem is, how do we generate these ordered pairs that we're going to connect? Okay, well, to get a visual here of what we're going to be doing, okay, let's just say that we do have this little short slope segment that we created because we have the derivative. We're given the derivative, and then as such, because we have the derivative and we have an initial condition, that's how we generated the little short slope segment. Okay, so remember this right here is the x-coordinate of 1. Okay, so we do have the ordered pair 1, 3. Now, the thinking is this. Let's move off of 1 just slightly, some delta x amount. Okay, you could either move to the left or the right. It just depends. Okay, I'm just going to move to the right. Okay, let's just say our change in x, which will be given to you, or delta x, sometimes called h, your step size horizontally speaking, let's just say that your step size is 0.1. So if I move 0.1 to the right, and y'all work with me, I know this isn't drawn to scale, but for what we need to see, this is the best I can do. Okay, let's say our step size is 0.1. Okay, so which means from the point right here, 1, 3, I'm going to travel horizontally 0.1. Okay, and then what I'm going to do is I'm going to travel vertically, okay, until I get here on the tangent line. I don't know if you can kind of see it, but the tangent line pulls away slightly from the curve here. So just imagine, if you will, I'm going to move 0.1 over, or whatever your step size is, and then I'll travel vertically until I intersect the tangent line there. So let me back up. All right, so now we have a new point that's on the tangent line. And so what we're going to do is we're going to actually find a tangent slope, a little short slope segment at that point. So think about it now as this being our initial condition, our new point, our new initial condition. Okay, plug those values into the derivative, get a slope, and from this point that was on the previous tangent line, we're going to draw another tangent line as indicated by the derivative. Okay, so starting the whole process over again from this point that I had, I'm going to move delta x, or 0.1, and I'm going to travel vertically until I get to and I rest upon the new tangent line. So now I've got this new point right here. Okay, we start the process all over again, meaning take this new ordered pair, plug it into the derivative, get a short slope segment, okay, move off of this point delta x and travel until you get onto the tangent line, okay, and create a new point. Okay, again, new point here, plug it into the derivative. Okay, maybe it's more steep. Okay, so now that it's more steep, we're going to travel to the right, our delta x amount, travel up until we get to the tangent line. And you can see how the little points are going to follow. The points are going to follow the solution curve. If every small increment, horizontally speaking, we stop, find the y coordinate or find the point on the tangent line, and then we reevaluate a new slope. So we're actually carving out these little short slope segments, creating them or connecting them with some points that are on the tangent lines. And then after you connect them, you should see that that's just a real good approximate for the actual solution curve. So hopefully you understand the thinking of what we're going to do. Now the mechanics is just kind of robotic. So let's look at an example of how we're going to use Euler's method to approximate a solution curve that we couldn't otherwise find by separating the variables. Okay, consider that our initial point was x sub 0, and y sub 0. So we're just going to consider that our initial condition, 1, 3. Sometimes you'll see the subscripts and sometimes you won't. Sometimes you'll just see x comma y representing your initial condition. Sometimes you'll see it this way as well. Okay, and then let's just say that we had some particular derivative that generated these little short slope segments here. And sometimes in notation, you guys will see that derivative written in this format right here. That's kind of crazy here. Okay, you'll see it something like this. So this represents a derivative. You'll be given that, and that represents an initial condition. Okay, and then also you might be given, well, you need to be given the step size. How far over horizontally are you traveling? Okay, in this case it was 0.1. And sometimes you see that represented by h, sometimes you see it represented with dx, and sometimes you see it represented as delta x. So this all has to be given in order for you to apply Euler's method. All right. Here's the thinking. If we called 1, 3, x sub 0, y sub 0, okay, then how do we generate this point right here, this next point that's on the tangent line? Well, x sub 1 is actually x sub 0 plus h. And I mean, think about it for a minute. This is x sub 0 plus h. You're going to travel over horizontally. You're going to increase the x component by h. Okay, x sub 2, which means now, okay, after I've recalibrated, so to speak, okay, my x sub 2 is going to land to the right of x sub 1. So it's going to be my x sub 1 plus h. X sub 3, x sub 2, the previous x plus the step size. So these are your x values here. And you can go all the way down to an expression, an nth expression, where x sub n is equal to x sub n minus 1 plus h. So these are all the x coordinates of the points that I'm using to approximate the solution curve. Okay, well, for every one of these x's, I need y's. Okay, so over here, let me get an expression that represents the y's. Okay, so and y equals, okay, that's a little more tricky. Okay, think about the original y that we had, y sub 0. So if this is y sub 0, what representation do I have for y sub 1? Okay, well, y sub 1 is going to be, at least in this picture, an increase. Okay, y sub 1 is going to be what y sub 0 was. Y sub 0 plus how much I travel vertically. Okay, so y sub 0 plus. Okay, well, what is this vertical component right here? And in order to find that, we're actually going to be finding the product of the slope of the line, okay, times the change in x. So what I'm saying is the change in y is equal to the delta y, if you will. The change in y, dy, this right here, is equal to dx times dy over dx, the slope. And a real quick visual right here, think about this for a minute. If this is the right triangle, I've slipped out of here. If I want to know what this value is right here, and I'm saying this is 3, and this slope is 4/3, well, you think about it for a minute. This is rise over run. This is rise over run. Okay? If I'm running 3, then I've got to be rising 4. So this has to be 4. Well, how can I get 4? Well, I multiply the slope of the line times the change in x. And numerically, look at that. 4/3 times 3. You don't have to write this, just kind of watch. Okay, that's always going to give me the change in y to multiply dx times dy over dx. Okay, but sometimes the textbook calls it h, okay, and the textbook also calls the derivative in this format right here. So if you look at the textbook for a reference, you're going to see this kind of thing. Okay, but I could call it what I have here. I could have put dx times dy over dx. Okay, and actually this right here is going to be the slope at x sub 0, y sub 0, if I'm calling that the initial condition. All right, so how do I get the next point? Well, I do the same thing. Y sub 2, okay, this y sub 2 is going to be an increase in this y sub 1. So it's y sub 1 plus, okay, to get up here, I've got to multiply the slope, okay, times the change in x, and that'll give me the change in y. So now this time, I'm going to have the derivative evaluated at, to get the slope, x sub 1, y sub 1, this previous point. So I think you see where this is going. Y sub 3 is equal to y sub 2 increased by the change in x times the derivative at the new point, x sub 2, y sub 2. So this can continue. So y sub n is equal to y sub n minus 1 plus h times the derivative, okay, at the last point, x sub n minus 1, y sub n minus 1. The calculations aren't going to be difficult. It's just the notation. And I think a table, which I'm going to draw here in a second, a table is going to help us with our examples. Oh, consider that you were given y prime equals x minus y. Let's say that's our derivative. All right, if you look at this just real quickly, you guys can see I can't separate the variables. I can't add or subtract anything. All I can do is multiply or divide to both sides of this equation. So this is dy over dx. Okay, these are going to have to stay together. So there's no way I can get this y over here without taking x with it. So I can't separate the variables to get a good look at, a peek into the solution to this differential equation. So what I'm going to have to use is Euler's method to help me get some points to plot so I can kind of see what the graph looks like. Okay, I told you guys you're going to be given a derivative. Here you are. You have a derivative. You're going to be given an initial condition. That's a point on the solution curve. You decide how you want to name it. X sub 0, y sub 0, whatever. Okay, your delta x, h, dx, however you want to call it. Your step size is 0.1. Okay. So what I want to do is I want to approximate, find an approximation, find an approximate for the function evaluated at, say, 0.4. I want to get an approximate value for the function at 0.4. Okay, with all this information. Well, if I'm starting at 0 and my step size is 0.1, think about how many iterations that is, how many steps that is. To go from 0 to 0.4, I'm going to have 4 iterations, if you will. So let's build a chart that's going to help us keep everything organized. It'd probably be better if I would just import a table and fill it in, but I think this will be good for right now. Okay, look at the headings. This is the ordered pair you start with, the initial condition. We want to document what is our step size. Okay, we want to record our derivative, that's given. So these first 3 things are given. Then we actually want to do some calculations, and then we want to generate the new point that's on the tangent line. All right, so here we go. Okay, for our example right here, we're going to start with 0, 1. Okay, we're going to record delta x to be 0.1, and the derivative y prime is x minus y. Okay, so now let's find the change in y, because it's easy to find the change in x, but let's find the change in y. So it's 0.1 times the derivative evaluated at, that should be 0.1, 0, 1. So that's our point, 0, 1. Let's plug it in here. So when I plug in, this is x, this is y, 0 minus 1, I get negative 1. Do the calculations. I'm going to get negative 0.1. That's our change in y. So actually we're not going up, we're going down. So the graph must be falling because we have a negative slope. All right, so here for our new ordered pair, think about what we started with, 0, add 0.1. So here we're at 0.1, comma, we started at 1. We're going to decrease it by 0.1, so we're actually at 0.9. So that's one step size. This would be an approximation at 0.1. Remember, we're trying to approximate the functional value at 0.4. Okay, start the whole process over again. So here in the last column, this ordered pair, it becomes the ordered pair in the first column in the next row. Usually these are no calculator questions, but they'll only have you do these iterations maybe 2 times, 3 at the most. Okay, I could continue to fill down column 2 and column 3 because it's always going to be the same. All right, so let's come over here. Delta x, always 0.1. Okay. Now right here, using this new ordered pair to create a new slope segment off of that point, let's plug in 0.1, 0.9, negative 0.8. So the slope's negative, the graph's still decreasing. Let's come over here. Oh, let me come back here and multiply these two. Okay, the product of those two, negative 0.08. Negative 0.08. Right, so coming over here, we've just increased 0.1 by 0.1, x plus delta x. So my x is here, delta x is here, so this is going to be 0.2. As a matter of fact, the next one's going to be 0.3, and then my fourth iteration is going to be the 0.4. All right, coming back up here, how do I get y plus delta y? Well, I take y, 0.9, and I add negative 0.08. So that's going to actually be 8.92. How about, oh my goodness, 0.82. How about 90 minus 8 is 0.82. There you go. 0.82. All right, so now this is our new point, calibration point. This comes over here. Okay, because I see I need to do a few more iterations, I'm going to bring this down. And I'll bring this column down too. All right, so here, change in x times the slope gives me the change in y. So times, okay, right here, 0.2 minus, because that's what the derivative is. I'm not always going to take x and subtract y, only because that's the derivative. Every derivative is going to be different. And what you do with these numbers is determined by the derivative. But for this one, 0.2 minus 0.82 is going to be negative 0.62. So that product is going to be negative 0.062, negative 0.062. Okay, as far as an AP test and these types of numbers, usually Euler's problem is the Euler's question doesn't allow you to use a calculator, but they only ask you to do 2 iterations, and the numbers don't get this detailed. All right, so jumping over here, let's find the y coordinate. So it's the previous y, which is 0.82, increased by, or if you will, decreased by, negative 0.062. So I'll just subtract these 2 numbers. And that results in 0.758. I said it's not going to be that tedious. And we'll do this one more time to accomplish the goal of approximating the functional value. Okay, so let's see what the y coordinate is, because that's the answer to the approximate question. All right, so let's go ahead and record this new point over here and go through the process again. Okay. So using this as our new base point, drawing a new short slope segment off of it, 0.1 times 0.3 minus 0.758, so negative 0.458. Whew. So let's multiply here. So it's going to be negative 0.0458, and that's what we're going to add to the previous y. So I believe the result of that is 0.7122, 0.7122. So at this point, if you will, I've done 4 iterations. If I'm approximating the functional value at 0.4, my x-coordinate matches the input. So therefore, I'm going to say that f of 0.4 is approximately 0.7122. All right, so this is a little bit of background about what Euler's method does for us. It allows us to generate a bunch of points that we can then plot, connect, and they approximate the actual function that we can't find because perhaps we're not given a separable differential equation where we can separate variables.